Hi everyone, welcome back to my number sense series. In this video we're going to talk about numbers ending in 5 squared. So on the board behind me I have 5 squares listed out. These are the first 2-digit numbers ending in 5 squared. And you might be able to see a pattern in some of them. And one part of the pattern is quite obvious. It's that all these numbers end in 25, as you can see. But the other part of the pattern might not be so obvious. It's the digits that aren't 25. So we have 2, 6, 12, 20, and 30. And so you might have already been thinking about this a little bit if you saw this in the thumbnail. And I'm sure some of you have already figured out what it is. But if you haven't, and I don't expect you to have, the pattern goes like this. This 2 is actually 1 times 2. And this 6 is actually 2 times 3. And this 12 is actually 3 times 4. This is 20 is 4 times 5. This is 5 times 6. And you'll notice that these start with 1, 2, 3, 4, and 5. So you can see that it'll always end with 2, 5. Well, we can conjecture that it'll end with 2, 5. And the digits that come before this will be the first digit times the number after it. So if we wanted to kind of infer what 65 is based on the sequence, what we would do is we would put a 2, 5 at the end. And then the digits before that, we would do 6. 6 plus 1 is 7. 6 times 7 is 42. So based on this, we've kind of guessed that the answer is 4225. And this is actually correct. And this is actually the correct pattern. But why? Well, this pattern can be derived from FOIL. FOIL, recall from the last video, allows you to expand the product of two binomials. A plus b times c plus d equals the product of the first terms, a and c, the outer terms, so a and d, the inner terms, which is the I, so b and c, and the last terms, so b and d. And you add them all together, and that is FOIL. And in last video, we used FOIL and separated 2-digit numbers based on their units and their tens, and we use FOIL like that in order to multiply them. Here we're going to do the same thing. So let's try to prove this identity. But let's look at one of the cases first. For example, 35. How can we do 35 squared using FOIL? Well, we could write, first of all, 35 squared is obviously 35 times 35. So we'll write 35 as 30 plus 5, as we would have in the last video. So it's 30 plus 5 times 30 plus 5. Now we'll use FOIL. So FOIL would give us 30 times 30 plus 30 times 5 plus 30 times 5 plus 5 times 5. And some of you might be able to see where this is going. But we'll see that we have a 30 times 5 and another 30 times 5. 5 30s and 5 30s is 10 30s. So this is actually 30 times 30 plus 30 times 10 plus 5 times 5. But 30 30s plus 10 30s is just 40 30s. So this is 30 times 40 plus 5 times 5. And here it might immediately become obvious that this is where our 12 comes from, 3 times 4. And this 4 is here because we added a 10, and this 10 was from the 2 5s. In other words, it's not a coincidence. These 2 5s are always going to be here, and they're always going to add that 10. They're always going to make it so that the first few terms of this number are going to be 3 times 4. They're going to be 4 times 5. They're going to be 5 times 6. For example, we can see that if we also do it with 65 squared, we'll get the same thing. But another way to kind of think about it might be using a square, because a number squared, well, it's called squared because it's the area of a square. So it might make sense to think about it like that. For example, let's consider the number 65 squared. So we would like to find the area of a square that has side length 65. 65, we're again going to split up into 60 plus 5. And what that looks like here is we're going to draw these. So this is going to not be to scale, but you'll get the idea. So what's going to happen here is this is of length 60, this is of length 5, this is of length 60, and this is of length 5. And so the area of the entire square is the same as the area of these 4 pieces added together. Now what I can do is kind of rearrange these pieces. So this is a square, this and this are rectangles, and this is a smaller square. So what I'm going to do is take this rectangle and move it over under here. And so I can kind of just imagine as like getting rid of this part, and I'll add it back over here. So that's what that looks like. So I just added another rectangle that's identical to this one under here. So now what this is it's this rectangle plus this little square. Now this rectangle has width 60, but it also has length 60 plus 5 plus 5. So it has area 60 times 70. And then the rest is just 5 times 5, which hasn't changed, so it's 25. And here you can see this 6 and 7 pop up again. It's like n and n plus 1. And you'll see that the reason we have this is because of the 5s in the units digit. In other words, this trick is going to work for any number that ends in 5. So let's try with another example, like 85 squared. Based on everything we've done so far, you would predict that 85 squared would be, okay, well, first of all, let's end it in 25, because that's not going to change among these numbers. So end it in 25. And so now we know for certain that the first few numbers are just going to be 8 times 9, which is 72. So it's going to be 7225. Very easy. Now, of course, this doesn't only work for 2-digit numbers. This can work for, as I said, any number that ends in 5. So we could expand to 3-digit numbers, 4-digit numbers. But let's see a basic 3-digit number example first. So, for example, 105 squared. What would you predict that 105 squared is? Well, the way we would do it is we would end again in 25, and now the first few preceding digits are going to be this 10 times 11, which is going to be 110. And the reason this still works is because we can really think of 100 just as 10 tens. And then the proof goes very, very similarly to all of these because we really just have 10 tens, not 100, if that makes sense. And so we could do this with like 135 as well. 135 would end in 25. 13 times 14 is 182, so it would be 18225. Now, they might also give you some like monstrously huge number, or at least some monstrously huge number for squaring. For example, they could give you some problem like 9,995 squared. And if you don't know this trick, this might seem like pretty much impossible to do in your head. But once we know this trick, it becomes super easy because what do we know? It's going to end in 25 again, obviously. And now, what are the first like 6 digits? Well, it's going to be 999 times 999 plus 1. And 999 plus 1 is 1,000, which is so nice to multiply by. And so 999 times 1,000, so our first 2 digits are just going to be 999000. And that's it. So this trick for squaring numbers ending in 5 is so powerful. This is absolutely critical to know. And if you watched our last video, you might actually remember a problem, 54 times 56. One part of doing that problem in 2 seconds flat is knowing this trick. The other part is difference of squares, which we'll cover in another video. But just know that this trick is so crucial to the rest of number sense. And it's really not that hard to remember. It just comes from if you can understand where you derive it from. Thank you guys for watching. I'll see you in the next one.